Hello, Stats 300, and this is Mr. Gonzalez. And I would like to do some problems from the assignment side of things, homework 7.3. And I just did this lecture an hour and a half long and found out this did not record my voice. So I'm a little low on energy now. But I'm going to try to do it again. Anyhow, here we go. So, before I do these problems, I would like to do my own take on this lecture and maybe clarify some things because this is 7.3 sampling distributions and the central limit theorem. I think can be a little bit tricky. So, let's take a look at my own version of this lecture. So it's going to be sampling. Sampling distributions and the central limit theorem. So let's first just talk about distributions in general. The distribution that we've been kind of honing in on a ton, of course, is the standard normal. Not the standard normal, just the normal distribution, right? And the normal distribution is great because it is symmetrical, and the normal distribution can be converted into the standard normal, which means which would mean that the mean, the median, and the mode are all at the same location, which allows us to use z-scores, which allows us to use the tables and get all this great information. So it's really a big deal if a population has a normal distribution. But, the thing is not everything has a normal distribution. You have, we looked at some of them, look like that, which would be skewed. And that one is what, skewed to the left. We had some like that skewed to the right. But the point here is that not all populations come from a normal distribution. And so if there's a way we could connect these skewed or different types of distributions and get them to be super close or approximately close to a normal distribution, once you do that, now you unlock the standard normal and z-scores and all that. So bullet point number 1, just to kind of start breaking down this whole sampling distributions idea. We sample the population by and we talked about this before, by performing a simple random sample. Okay, sample size. That's just the size of the sample that we take, and we use n, which equals the sample size. For each sample, so I'm just giving you some thoughts here. For each sample, which is, grouping, that has size n, we can do things to it. We can calculate within this sample, right? Within this grouping, we calculate the mean. We can calculate the variance. We can calculate the standard deviation. Okay. So given a population that has a mean, and for population we use mu, given a population that has a standard deviation, for population standard deviation we use, whoops, what happened there? Something happened with a pen. We use sigma. Okay. So remember population we use mu and sigma. Okay. So just to kind of get a sense of what's happening here, let's just take an example of some population, and it might be a normal or it might be not normal. Let's just do something that's not normal, something like something that looks skewed, something like this. Right, so it's not perfectly normal. And maybe the mean is, like over here somewhere. Anyhow, what we can do now, this is going to be some population. It could be the population of the heights of men in the United States. It could be whatever, just some population. So what we want to do is we want to sample from that population. I'll just call this sample number 1. And what happens in a sample? Well, if we're trying to figure out something about the average heights of men in a population, or something like the average height, we might sample, let's say, 35 men. So this sample size n is going to equal 35. So when you sample, you're going to get a value number 1, like maybe a guy's height, and you simple random sample another, get another height, another value. You do that all the way down to value number what? 35, because we're doing n equals 35. Okay. And then you get another sample. Sample number 2. Value number 1, 2, 3, all the way down to value number 35. And you get another sample. Same thing, value 1, 2, 3, down to value number 35. And you keep on doing this, you can get another sample. But the point is that once you have a sample, right, you can do something with this information, right? One of the things we do is we add up all the values and divide by 35, and that gives us a sample mean. So that x bar is just what we like to use, the variable that we like to use that gives us the mean from the sample instead of the mean from the population. So this is the mean from a sample. And then right here, our second sample of another 35 values, we can add them up and divide by 35 and get a sample mean. And our third sample, we could add all those values up and divide by 35 and get a mean. And it turns out that these sample means, it would be crazy luck for them to all be the same. They're not going to be the same, right? They're not going to be the same. So, like, let's say back here in the population, someone said, I want to know what's the average height of men. So I want to know the mean of the average height of men in the United States. Excuse me. Well, that's going to be really hard to do because there's just such a huge number in a population like that. So the next best thing would be, at least starting wise, would be to do a simple random sample. Randomly sample some people. We got 35 people, and we get the mean of that, and that kind of gets us, at least we get a place to start from. And then you do it again, and then you do it again. And that really starts to give us some great information about what the actual population mean is, right, from the sample mean. Okay. What other things can you get from this information? Well, X bar is the X bar is the mean from these values, but you could also then go through and find the mean of all these X bars, the mean of the mean, which that starts to sound a little bit confusing, but you can get all those X bars and then you can find the average of that, the mean of the X bars. Okay. And then you could also go through all those X bars that you found and find the standard deviation of those X bars. So it's gets a little bit confusing. So let's continue with this idea here. Let me start a new page. Okay, so we get this central limit theorem. I'm supposed to say CLT. Wow. Okay, central limit theorem. Okay, now this says if your sample size is greater than 30, then there's some great things we can say. Then, now this is a mouthful, then the mean, it's what I just said actually, then the, wow, that looks funny. I got to start that over again. Then the mean of the sample means, remember on the previous page that was those sample means were in red, X bar, right? Of the sample means is going to be equal to the population mean. So there's too many means in that sentence, but basically what that's saying, so the mean of these sample means is going to be equal to the mean of the population. Okay. Now remember, for this to work, this is a central limit theorem. For this to work, either you have to be sampling from a population that is said we know is normal, or if we don't know if it's normal, it might be skewed. In order to get around that, we'd have to make sure our sample size is bigger than 30. If you do that, then we can say that the mean of the sample means, right, finding the average or the mean of the sample means, is going to be the same thing as a population mean. That is huge because now we can say something about the population mean, even though that's a hard thing to find, right? You don't have to add up every single person in a population. So let me highlight that. So if you know nothing about a population, and you sample it, using a simple random sample, i.e. how would you sample it? Well, kind of like I just showed the other page. I'm not going to do that whole thing again, but right, take a sample number 1, sample number 2, sample number 3, sample number 4, and so on. And then within each one of those samples, we want that sample to be bigger than 30. If you don't know what the population it's coming from, then each one of those samples, we can add them up and divide by how many, the n value, and we can figure out the average of each one of those samples, called the sample mean, or X bar. Okay. Then, just kind of restating what I said before, then you average, or take the mean of the values of the x bars. And that is, use this notation. Let me try that again. We use this notation. That's the mean of the x bars. So let's see. Then you average the values of the x bars, which is the mean of the x bars, and that will equal the population mean, right? Which is mu. Or I should say very closely. Okay, so just to highlight this a little more, so by sampling, we can learn something about the population. That was previously unknown. Before. Okay, so I also want to point out, let's see, where is it at? In our notes, I kind of reorganized the way that the book has it. I wanted to organize in a way I think that was a whole lot better. And that is, I've got all the central limit theorems for the sampling mean that we're talking about right now. This right here is 7.3. It's all in the same box. But essentially what it's saying is, if your n value, if your sample size is greater than 30, then the sample means distribution is approximately normal, which is awesome because then you could turn it into z-scores. And looks like we have something in the way there. And you might not know the population mean, but you can get that by just getting a bunch of samples, finding the sample means and the mu of the sample means, and that is going to be equal to the population mean. That's nice. And you can also figure out the population mean because you could get you could also get the standard deviation of the population right there by getting the standard deviation of the sample means, which is something you can get by sampling. And that is going to be equal to the population standard deviation divided by the square root of n, right? So once again, and I'm going to talk about that coming up. And also, you can find z-scores from sample means. So you can get that from sample means. That would be the z-score, the same z-score we were talking about before that has the same z-score tables. You take a sample mean minus the mu of the samples, but you don't have to say that because, why? Does this not have to be the mean of the sample means? Because those are two equal things. So they just say, I'll just make it the population mean, and then divided by the standard deviation of the sample means. And that will give you the z-scores, which gets us back to what we were doing in 7.1 and 7.2. Okay. All right, so let's get into that in a second here. Go back to our notes. So by sampling, okay, so let's say central limit theorem. So central limit theorem also, what can we say? Also, and I'm going to restate what I just said up there looking at our notes. Also, I can figure out the standard deviation of my population figure out the sigma by just sampling data. Okay, so once again, we've got our standard deviation of the sample means equals the population standard deviation divided by the square root of the sample size. So with algebra, right, because it's just these are all variables, if we have two of the three, we could always isolate the third, right? So very often, the standard deviation of a population, sometimes that can be really hard to get. Because think about it, if I was trying to find like the average height of all males in the United States or the average height of all males in the world, you would have to calculate the standard deviation with all those people. That's really, really tough. On the other hand, if you sampled and made sure your sample size was greater than 30 and you found the your X bar, oops, darn it, just switched. You found your X bars, right? And then you found your standard deviation X bars, because that's a number that you can calculate. And so this is a known number, and then you would know your sample size. So that is and the square root of sample size, that's a known number. And then if this was your question mark, right? This is the thing you're looking for. You just mathematically isolate the sigma. So once again, you could actually find out the standard deviation of the population, just by using sample data. Okay. That's kind of one of the big points of the central limit theorem. Let's talk about the central limit theorem a little bit more, because it does take a little time to kind of get down. Let me just start a new page. Central limit theorem. Okay, if the population is normal, then the sample means will also form a normal distribution. And then that's, we keep on talking about sample size needs to be greater than 30. But if you're sampling from a population, that's normal, then the sample size doesn't have to be large. So this is, it's going to give us the sample means. The sample means will also be normal, even with a small sample size. That's because the population was already normal that you're sampling from. So this is kind of what we're talking about. Let's say here's the population. And it's coming from a nice normal distribution. Okay, so then you find your sample, another sample, another sample, another sample, right? So you take a bunch of samples. Then each one of those samples, you figure out the mean of those samples. So the sample means, you create a distribution. And it will be normal. Why will it be normal? Because it came from a normal population. So, when you started stacking these sample means up, this is a histogram, a dense basically a super dense histogram. And so, but when you start stacking up these, data, you're going to find out that it creates. I'm going to run out of time here doing this. My hand's cramping up actually. Actually is cramping up because this is the second time I've done this lecture because the darn thing sound was not working. I'm still a little bit mad about that. Anyhow, so this came from a normal population, and so then when you took the samples and then took all these sample means and then made the distribution, it's actually going to make a normal distribution, and that's even if your sample size is small. Okay, so that's something that's kind of interesting. Let's see, let's get rid of that, and I just want to put a notation that, remember, this is all X bars, so this is not your population mean, this is your population of the X bars, right? I'm sorry, this is your mean of the X bars, whereas since this is from your population, this is just your mu, the mean there. Okay, so this is the mean of the X bars, and this new notation that we're introducing. But even more shocking than that, even more impressive, triple star. If the population is not normal, but we use a sample size that is what? That is greater than 30. Then the sampling distribution of the sample means remember the sample means are these little X bars we're talking about, of the sample means will be approximately normal. Approximately normal distribution. Okay, so that's the central limit theorem right there. Central limit theorem. It says if the population is not normal, but we use a sample size that's greater than 30, then the sampling distribution of the sample means X bars will be approximately normal. And once it's normal, we can then convert them to z-scores and use our z-score, our z-table. So it just opens everything up for us. So that is really great. We can use this stuff even on populations that are not normal. Example. And then I got to get to our homework here. So, for instance, IQ. So IQ testing. Oh, what happened? It just jumped on me. IQ testing. IQ test. They basically make the IQ test so it has a normal distribution, and the mean here is going to be 100. So the mean of the IQ test for the general population the mean is at 100. Okay, so what if we get a skewed population? So this is a new population. What's the population? Population. Who are we checking out? Okay, this is going to be a population. I want to study the IQs of Stanford students. So, I mean, we kind of expect the IQ of Stanford students to be skewed compared to our normal general population, just because to get into Stanford, you have to have a lot of money, but you also have to, you have to have really great SAT scores. You have to have super high grades. So it makes sense. It makes sense that their population is going to be. So if this was, let me try that again. If this was, right, 100, the old mean for the general population, those Stanford smarty pantses are probably going to be out here somewhere, probably going to be skewed somewhat, right? And so they're probably going to have, their mean is going to be maybe out here somewhere. Let's say population mean is 125. So what I'm trying to say here is using the central limit theorem, even though we have this skewed distribution, if I take my sample and that sample size is greater than 30, and I take another sample and the size is greater than 30, so they're all going to be greater than 30, right? Another sample, another sample. And with those samples, they're going to be more than 30 data points that I can add them up and divide by whatever the sample size is, and I can get these X bars, right? The mean of the sample, or sample means. And then I could make my sampling distribution. Can make my sample distribution, which would, I could make my sample distribution. And what's interesting about this is that when I take all these sample means and I make my sample distribution, even though this was skewed from the population, this sample distribution will be a normal distribution. And in this case, this sample, the mean of the sample means is going to be 125. And that's maybe not super intuitive, but that is kind of the cool thing here. Let me make that another color so it doesn't look like the same thing. There's my population mean over here. Population mean is 125. And when you do your sampling, your sample mean is going to be the same as the population mean. And so that's a huge, huge thing. Meaning I could figure out my sample mean and, just erased. This thing keeps on switching over. Oh, I could hit the back button, okay? So that is a huge thing because I could find the mean of my sample means, and that number is going to be the same as the population mean. Huge. Okay, and I have a note here. Let me just make sure I said everything I want to say. Why is this so important? If I sample a population with the sample size greater than 30, the distribution from the sample mean will be a normal distribution like I just showed here, or close to a normal distribution, which allows us to use the empirical rule. It allows us to use z-scores. And by the way, the z formula for this would be sample mean minus, and once again, we usually say sample the mean of the sample means, but because that's the same as the population mean, you don't have to do that. You can just take the population mean and divide it by the standard deviation of the sample means. So we can get z-scores. We can get this huge that we know. I just said it, but we know that the mean of our sample means is the same as the population mean. We also know that the standard deviation of the sample means is going to be equal to the population standard deviation of the square root divided by the square root of the sample size, okay? All this stuff I have for you back here, nicely organized, and this formula sheet for 7.3, okay? All right, this is the second time. If this sound does not work this time, I'm giving up. Well, I won't give up, but I'm giving up for tonight because this is too many times. So let's go back up here to the top of our page. Now, once again, we're doing assignments, the assignment side of things, homework 7.3. And after you get 7.3, 7.4 should like fall right into place. Should be really quick and easy because it also uses central limit theorem. All right, number one. A population has a population mean of 19 and a standard deviation of 22. They want us to find the mean of the sample means. Well, we know some formulas, don't we? We already know as long by the central limit theorem, as long as my n value is greater than 30, I don't care what population it comes from. And they told us a population. They didn't say normal population. So we don't know what the population looks like. But the fact is that my sample size is 100, which is definitely greater than 30, which means I get to use all the formulas from the central limit theorem. First one would be that the mean of my sample means is equal to the population mean. So the first thing they want us to do is find the the mean of the sample means. So the mean of the sample means is equal to the population mean. That's going to be 19. Done, 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 done. The next thing they want is, what is the standard deviation of the sample means? Well, the formula for that, once again, just so you know where to look, formula sheet, formula sheet, formula sheet, it is right there. So that is just the standard deviation of the population divided by the square root of the sample size. Well, they give us that information. They give us that this population standard deviation is 22. And we also know that the sample size is 100. And you just need to take the square root of that. And the square root of 100 is 10. And so the standard deviation of our sample means is going to be 2.2. All right, next question, number 2. A sample size of 125 will be drawn from a population. So once again, the sample size is greater than 30, so we're allowed to use the central limit theorem even though we don't know what the population looks like. Now it's important to label your variables, meaning, is this the mean from the population or is this the mean from our sample? Because those are two different things and two different variables. And it says a sample size of 125 will be drawn from a population with a mean of 50 and standard deviation. Well, they're talking about, this is saying it's the population. So be really careful that, when you're organizing data, population. Information from the population, well, the mean from the population is 50, and the standard deviation from the population, sigma, is 17. Okay. What are we looking for here? A. So find the probability. Well, before we do this, we're going to need some more information. So some of the things we're going to need is from the sample, right? So from that sample, where'd it go? Sample, n equals 125. Also, from the sample, we know that the mean of the x bars, or the mean of the sample means, is going to be the same as the population. The population is 50. Population mean is 50, rather. So the mean of the sample means is also 50. So we got that. The other thing we need to calculate is the standard deviation of the sample means, right? And, we know where to look for that. That's on our formula sheet. And that is just going to be the population standard deviation, which is 17, divided by the square root of the sample size, 125. And when I put that in my calculator, I get approximately 1.5 0.5205. Okay. Question for A. Find the probability. If they say probability or they say proportion, remember that's the area under the standard normal curve. So find the probability that x bar, that the sample means will be between this sample mean and this sample mean. Round your answer, final answer to 4 decimal places. Okay, so really what we need to do is we need to convert, I'm going to use some colors here, we need to convert this sample mean into a z-score. So the formula for that is our sample mean is 49 minus the population mean of 50 divided by the standard deviation of the sample means, which is 1.5205. And when I subtract that and divide that, I get approximately negative 0.66. And then I need to find my z-score for when the sample mean is 52. So sample mean of 52 minus my population 50 divided by the standard deviation of my sample means, which is 1.5205. Gives me an answer of approximately positive 1.32. All right. So now, I don't have a lot of space there because I got a part B I got to do. Okay, so let's see if we can squeeze this rest of this problem into this little space right here. I think I can do it. So you know that this is going to produce a standard normal curve that always has standard normal curve 0. And using my color, I've got negative 0.66 and I've got a positive 1.32. And let's not forget, what do they want us to do? They want us to figure out the probability that your x bars will be between those two, between these two x bars. Well, we turn those x bars or sample means into z-scores, and we want to figure out what is the probability that we're going to land between those two. Now that we've changed them to z-scores, I can look them up. Now we're back to Easy Street doing problems just like we were doing in 7-1. If I look up that z-score on my z-table, I will find that the area to the left of that is 0.2546. And if I look up that z-score, I will find the area to the left of that z-score, which I will show with this, is 0.9066. And so I know I take the larger area of 0.9066 and subtract out the smaller area, which is 0.2546. I subtract that out, and that gives me a result of 0.652, which is the area of this shaded region in between the sample means of 49 and 52. There's our answer. Once again, let me kind of clean that 5 up a little bit. Answer is 0.652. Okay, that does not leave a lot of space for part B. Part B is asking, find the 35th percentile of the sample mean x bar. Okay, well, let's do it. So what this is, they're finding the 35th percentile, and remember how percentiles work. 35th percentile means if I put a mark right there, 35th percentile means that 35% of the data is below this position. That means when they say 35th percentile, that means the area is 0.35. Okay, so what I'd like to have here is the X bar that belongs there, right? And this right here is the mean of the X bars. So I'd like to know the X bars, but that's not going to show up on my Z table. So that's a little too positive thinking there, right? We're not going to get there that fast. However, if I look up, so remember, I don't have my Z table with me because I've done it quite a few times. I'm hoping you can remember how that goes. Now you look, this is area. So look on your Z table in the body, the middle of the Z table, for an area of 0.35. And of course, you know, there's 4 decimal places in there. Try to get as close as possible. And, you know, it's not perfect going backwards like this. When I looked it up on the Z table, it was somewhere between 0.38 and 0.39, I believe, something like that. So I said, oh, let's say it's in between there. So it's going to be approximately negative 0.385. Now that's a Z-score, and I really wanted the X bar that's located there. So just like before, I could translate, like before we translated raw scores to Z-scores and Z-scores to raw scores, you could do the same with X bars. So, and remember that formula. I already showed that to you. Let's look at it really fast. It is right there. Okay. So here's how you can translate this Z to an X bar, to a sample mean. So it would say that Z, which is negative 0.385, equals the X bar minus the mean. And in this problem, our mean is 50. It's 50 divided by the standard deviation of the sample means, which is 1.5205. And I need to do a little bit of erasing here. Come on, there it goes. Okay. How do I solve that? Well, algebraically, we're going to multiply both sides by this denominator, clearing the fraction. So we multiply 1.5205 on the right, and you also have to multiply the same value on the left, 1.5205. When you do that, right, common factors will reduce, leaving us with X bar minus 50. And on the left, we multiply these two values, and we get approximately negative 0.5854. I'm going to say approximately. And then you simply add 50 to isolate the X bar, add 50 to both sides, and you get a final answer. Get a final answer of X bar is approximately equal to 49.41. And that's the X bar, or that's the X bar. What was the question? Find the 35th percentile of the sample mean. Okay, so the 35th percentile of this sample mean is going to be 49.41. Let's take a look at question number 3, almost there. First question, a sample size of 7. Now that should be a little bit alarming because we know to use the central limit theorem, sample sizes must be greater than 30. Will be drawn from a red pencil will be drawn from a normal population. So now we don't have to worry about that because it's coming from a normal population. And so that sets us up with the first question. A, is it appropriate to use a normal distribution to find probabilities for the sample mean? And the answer is yes, it is appropriate. Yes, it is appropriate. Why is it appropriate? Well, because even though the sample size is less than 30, the sample is from a normal population. Because the sample's from a normal population, we can have a small sample size and still our sample distribution will be normal. So is it appropriate to use a normal distribution? Yes, because we're sampling from a normal population. All right, let's do the next question, part B. And before we get started, let's go ahead and start taking some notes. Population. Let's see. A sample size of 7 will be drawn from a normal population. Now, they said from a population with a mean, so talk about the population, not the sample. Population has a mean of 63, and the population has a standard deviation of 15. Let's use the proper labeling variables. Mu is 63, and sigma, the standard deviation of the population, is 15. Okay, now how about sampling information? Well, they told us that the n value is a bit small. It's only 7, but it's coming from a normal population, so we're still good. We can use the central limit theorem, which allows us to start getting information we need, which would be the mean of the sample means is going to be equal to 63, the mean. And the standard deviation of the sample means, well, that's just going to be the standard deviation of 15 divided by the square root of our sample size 7. And when we throw that into the calculator, we get approximately 5. Try again, approximately 5.6695. Okay, now what? Well, they're looking, so this is the same problem as the last problem. They're looking for the probability that my sample mean will be between this sample mean and this sample mean. So I think we better turn those sample means into z-scores so we can put it on standard normal curve and then look them up in our z-tables. Well, that's going to be, the z-score is going to be the sample mean of 53 minus the mu, 63, divided by our standard deviation of a sample mean, which is 5.6695. So this will give us, let's see, this 53 minus 63 is going to give us a negative, approximately negative 1.76. Okay. Let's try another one. We need this other z-score. This other z-score is going to come from our sample mean of 73. So 73 minus a mu of 63 divided by the standard deviation of the sample means, 5.6695. That stays the same from here. This gives us approximately positive 1.76. Okay. So now we have converted into z-scores. So this is considered a standard normal curve. So it's got the normal curve, and even better yet, the mean is 0. We've got this negative 1.76. We've got this positive 1.76. And they're looking for us to find the probability that will be between those two values. So really between these two values. You're talking about that. Okay, well, we have them as z-scores, so that's awesome. And just like before, the same problem as before, we look this z-score up on the negative z-score table, and that gives us the area to the left, which is 0.0392. Then we look up this z-score, and that gives us the area to the left, which is all the way down there, including that. So it goes from here to here, and that area is 0.9608. And of course, if I want the shaded region, just like before, 0.9608 minus the green, minus the green, minus the green, 0.0392. And that subtraction gives us the answer of 0.9216, and that is the probability that we will get an x bar between 53, an x bar of 53 and x bar of 73. Very high probability, right? You can change that to a percentage. They didn't ask us to, so it's okay to leave it as decimal, but about 92, a little more than 92%. All right, going on to the final stretch. Like I said, this is the second time I've done this. I just did it consecutively because I just did the whole dang thing without any volume. So it was just 0 volume. I'd start over again after I finished the whole thing. Anyhow, finally, if appropriate, and it is appropriate because we're drawing from a normal population, so it's okay that our sample size is tiny. We're looking for the 83rd percentile. So just like before, our percentiles are, hold on a second, there's my standard normal curve. I would say 83rd percentile means that 83% of the population is to the left of this point. We are looking, what are we looking for? We're looking for, if we find the 83rd percentile of the sample means. Okay, so basically we're looking for the sample mean, the 83rd percentile of the sample mean. So we're looking for this value right here when the area under the curve is 0.83. Okay, so if I go to my z-score on my z-table, I look in the body of the z-table, or use a calculator, but look in the body of the z-table, and of course the z-scores go out 4 decimal places. You try to find the closest to 0.83, and if 0.83 is between two values, then I like to just go in between just to give it a little more value. But when we do that and we look this up, it's not going to be an x bar, right? What does it give us when we look at the area inside? Well, it gives us a z value. So this is going to give us a z value when we look up 0.83, and then we go to the outer edges of the z-table to get our actually z-score. We get approximately 0.955. Okay. Now, what I really want is I want to know what x bar is that. And we can do that once again by taking this formula that z equals x bar minus mu, mu, divided by the standard deviation of the x bars, right, of the sample means. So how much space do I have? I think I'm going to go down here. So what I can do is I can put down my z-score, which is 0.955 equals this x bar that I'm looking for minus the mean. We found out the mean, or the mean of the sample mean, the same thing, 63 divided by the standard deviations of the x bar, so that's going to be 5.6695. All right, algebraically solve this thing. It's almost there. 5.6695 gets multiplied on both sides. Whoops. 5.6695 gets multiplied on both sides. And when we multiply it on both sides, right, cancel common factors from the numerator to denominator, which gives us our x bar minus 63 on the right side. And on the left side, we calculate that this is going to be approximately 5.41437. And then we add 63 to both sides. And we get x bar is approximately 68.41. And that is it. Whew, that was a long run, especially doing it twice. Yes, I'm complaining. Anyhow, I hope that doing the extra lecture was helpful for you, all this extra stuff, because I really think if you get 7.3 down, 7.4 ends up being much, much, much easier, because 7.4 also uses the central limit theorem as well. I hope everybody is safe and staying COVID-free. I will talk to you soon, and take care and have a nice day.